This is video 2-1, Scientific Method, Units of Measurement, and Metric Conversions. So, in Chapter 2, Measurements and Calculations, calculations that you learn, the methods that you learn in this chapter, make sure you learn them well. You will be using those for the rest of the semester and also the rest of the year. So, these are really important skills that you need to learn. So, first thing we look at, scientific method. We're not going to spend a huge amount of time on this because you've learned this in basically just about every science class that you've taken so far. Okay. So, what is a scientific method? Logical approach to problem solving. Just a series of steps you should use to solve problems. Okay. First step, most of you know this, state a problem. But when you state a problem, it is based on observations, something that you used your senses. Next step, observe and collect data. Before you go and make a hypothesis, a possible solution to your problem, you want to make sure you go and collect additional data so that you're not just making a blind guess. Use your senses, use instruments, etc. Okay, now, what is data? Data is simply recorded observations. Once you make an observation, once you record it down, write it down, it's now data. Okay. Data can be one of two types of things. They can be qualitative, which is basically just a descriptive data. In other words, you don't put any numbers in. You say something's heavy, something's light, something's large. A color is a qualitative descriptive. Okay. Or quantitative. Quantitative, now you need to start putting numbers in. 10 grams, 2.5 milliliters, something like that. Next step, after you've gathered your data, form a hypothesis, which is a testable, must be a testable statement. It's a possible solution to your problem. Okay? But the key here is it has to be testable. Okay? Next step, testing. Test it. Now, how do you test it? Well, basically, you set up an experiment. Okay. Now, whenever you set up an experiment, you should always have two parts to your experiment. One part is called the experimental setup. And this contains the thing that you are trying to test. This contains your variable. The second part to your experiment should be the control. Okay. The control should be identical to your experimental setup, except that it does not have the variable in it. So all the factors in your experimental setup and your control should be exactly the same except for the variable. Okay. Ideally, you should only have one variable in your experimental setup. Okay. And you should do it a couple times, multiple times for consistency. Okay. Your last step, after you've taken your data, you've analyzed it, now comes theorizing, or basically drawing your conclusion. Okay. And your conclusions basically should only really be able to relate back to your hypothesis. Was it correct? Was it incorrect? Okay. Now, hypotheses, if they're related to or similar to each other, can turn into something known as a model. A model is basically something that symbolizes an idea or a concept. Okay, a model of an airplane is basically just that. Okay. Several related models can turn into theories. Okay. Theories cannot turn into laws for a simple reason. Okay. Why? Simple. Because of what they do. A theory attempts to explain a set of conditions that produce a certain result. Okay. A law states that a certain set of conditions will always produce certain results, but the law doesn't tell you why it does that. The law just says, if you have this set of conditions, this will happen. Okay. It may even show you what the relationship is, but it doesn't tell you why. Okay. So, a couple examples. The theory of plate tectonics. Plate tectonics, basically a way of explaining why we have earthquakes, why certain structures form on the earth, and the idea is because the Earth's crust is broken up into a bunch of different plates that can move. Okay, so there's an explanation. As opposed to the law of universal gravitation. The law of gravitation basically just says all objects with mass have an attractive force between them, and the size of that force is proportional to the two masses, inversely proportional to the square of the distances between the two masses. Okay? But it doesn't tell you why, so that's why that's a law. It just says, hey, here's your set of conditions, this is the relationship, but it doesn't tell you why the relationship exists. Okay, now, some people may say, well, why are some things not considered to be scientific theories? If something is a scientific theory, it makes falsifiable predictions about things not yet observed. In other words, the theory must have the ability to be proven false. Okay? A theory that makes no predictions that will ever be observed is not a theory. And predictions which are not sufficiently specific to be falsified are meaningless and likewise not going to be a scientific theory. Okay. Now, units of measurement. Okay. First thing we look at, temperature scales. Okay. 3 temperature scales that are commonly used. The ones that we are going to be using in this class, Celsius and Kelvin. We're not going to necessarily be using Fahrenheit, though we will mention Fahrenheit a lot because these are numbers that you're kind of used to dealing with. Okay. So, boiling points for water. Oops. Okay. On the Fahrenheit scale, boils at 212, water freezes at 32 degrees Celsius. Celsius, nicely used because freezing point of water is 0 and it boils at 100. Kelvin, we use 273.15 and 373.15 for the boiling points and the freezing points. Okay. Now, why the Kelvin scale? Sometimes it's called the absolute scale because there is something known as absolute zero. This is basically the coldest temperature that you can get to. Okay. Absolute zero on the Kelvin scale is 0. There is no negative numbers on the Kelvin scale. Celsius goes down to negative 273.15. That's the lowest temperature you can have in Celsius. Lowest temperature in Kelvin possible, negative 459.67. Okay. Now, what's the relationship between these 3 scales? Okay. Well, let's take a look. On the Fahrenheit, between the freezing point and boiling point, the number of degrees of increments is going to be 180 degrees up here. On the Celsius scale, between the freezing point and the boiling point, the differences will be just 100 degrees of increments. On the Kelvin scale, between the freezing and the boiling points, it's also 100 degrees of increments. Okay, so on the Fahrenheit scales, now these are degrees of difference. 180 degrees of difference is equal to 100 degrees on the Celsius scale, which is equal to 100 degrees of difference on the Kelvin scale. Now, let's go reduce everything by 100. We basically get that 1 degree change on the Kelvin scale is equal to 1 degree of change on the Kelvin scale, but it's a 1.8 degree difference on the Fahrenheit scale. So, in other words, if you went from 32 degrees Fahrenheit to 33 degrees Fahrenheit, you did not go from 0 degrees Celsius to 1 degree Celsius. That did not happen because 1 degree of increment here on the Fahrenheit scale is not the same as 1 degree of Celsius there. Okay, now, how do we convert between temperature scales? Simple. Okay. The Kelvin scale and the Celsius scales are identical in terms of increments. In other words, if you go up by 1 degree Celsius, you go up by 1 degree Kelvin. So, Kelvin is always larger. Just remember that. The Kelvin scale is always larger than the Celsius scale. So, take your Celsius, add 273.15 to it, you come out with your temperatures in the Kelvin scale. Okay. Now, the Fahrenheit scale, a little bit different because going up 1 degree Celsius is not the same as going up 1 degree Fahrenheit. You need to take your degrees Celsius, multiply by 9/5, then add 32 to it, and that will give you Fahrenheit. Okay. Now, some simple math like what you did on the worksheet. You should be able to take this equation right here and change it into this. That one's pretty straightforward. Just subtract 273.15 from both sides. So Celsius should be equal to 273, or Kelvin minus 273.15. Okay, this one you got to do a little bit more math. Okay, so first thing we do, subtract 32 from both sides. And then that should basically leave you with degrees Celsius times 9/5. Okay. Now to get rid of this, just multiply both sides by 5/9 and multiply this by 5/9. Fahrenheit stays in parentheses. That cancels out, that cancels out. So degrees Celsius should be equal to 5/9 times Fahrenheit minus 32. Okay, now where does 9/5 and 5/9 come from? Well, if you go 9 divided by 5, you come out with 1.8. And if you remember, this 1.8 was the factor difference between Celsius and Fahrenheit. So let's get rid of that so you can actually read all that stuff. Okay. So basically, remember how to use equations. You are solving for this, and this is what you have to be given. The things on the right side are what you're given. Okay, so if you're trying to solve for something on the right side, you need to rearrange the equations. So let's try a quick little problem. Normal body temperature, 98.6 degrees Fahrenheit. So what's this on the Celsius scale, and what's this on the Kelvin scale? So I need to go figure out what is the formula for Celsius going to be equal to. Okay, well, if we go back, we remember that. Oops, let's see. Degrees Celsius here was equal to Fahrenheit minus 32 multiplied by 5/9. Okay, so that's the formula we need to use. It's equal to Fahrenheit minus 32 times 5/9. Okay. Plug in our numbers, 98.6 minus 32, multiply by 5, divide by 9, and you should come out with, if we do our math correctly, 37. Now 37 what? It's 37 degrees Celsius. Okay, so your body temperature on the Celsius scale should be pretty close to 37 degrees Celsius. Now, what about the other rest of the problem, the Kelvin scale? Well, Kelvin we figured out was pretty simple. Kelvin was just going to be equal to degrees Celsius plus 273.15. Okay, and remember, Kelvin is always bigger than the Celsius. So if you forget, do I add or subtract? Well, if you're going to make it in Kelvin, make sure that the number's bigger than what you started with. So this should just come out to be 310.15 Kelvin. Okay, and Kelvin doesn't have the little degree symbol in there. Hey, density. Something you probably learned about before. Okay, density is basically just the mass per unit of volume. If how heavy is something per a unit of volume? Okay, so the word per basically just means divide. Okay, now you may want to get into the habit of writing it this way. Instead of using the slash, just use the divisor line. Okay, D is equal to M times V. And you should also be able to solve for the other variables. M is equal to D times V, and V is equal to, and if you remember the little trick I showed you earlier, you can switch diagonals. This is a fraction, D over 1. So D and the V just switch places, and you end up with M over D. Okay, the units. Standard units. Kilograms and cubic meters. Okay, the problem with using that is when you measure something that's relatively small, It doesn't have to have a very large kilograms, but the cubic meters will come out to be really small numbers. So you end up with large numbers using kilograms per cubic meter. Okay, it's good for measuring gases though, because gases tend to have really small densities. Okay, so more common units that we'll use. For mass, we'll use grams, and for volume, we'll use cubic centimeters. Okay, or grams per milliliter. Okay. Now, what's the difference between a cubic centimeter and a milliliter? They're basically the same. If you were to make a cube and fill it up, and the cube had dimensions of 1 ml, whoops, not 1 ml, 1 centimeter, 1 centimeter, and 1 centimeter. The volume is 1 times 1 times 1, and that's 1 centimeter times 1 centimeter times 1 centimeter. When you multiply numbers, that's pretty simple. You also multiply the units together. So 1 times 1 times 1 gives you 1. Centimeter times centimeter times centimeter gives you centimeter cubed. That's where those units come from. Fill up this box with liquid, pour it into a graduated cylinder. Its volume would be 1 ml. Okay, so that's where this equality comes from. Okay. 1 cubic centimeter is the volume occupied by a cube that measures 1 centimeter on each side. Okay. And remember this, denser objects will sink in fluids that are less dense than the object. Okay. So, density of water is basically pretty close to 1 gram per milliliter. Okay. If an object sinks in it, its density will be greater than that. If it floats, its density will be less than that. Okay. Objects placed in a graduated cylinder, 35.3 mLs of water. After the object sinks, the volume of the water rises to 46.8 mLs. If the object's density is 2.47 grams per cubic centimeter, what's the mass of the object? Okay. Well, what do we know? Well, initially, the water's volume is 35.3 mLs. Okay. Once you put the object in the water, the volume is 46.8 mLs. So, volume of the object must basically be the difference between those two. So, 46.8 minus 35.3, that will give you, let's see, 11.5 milliliters. That's the volume of the object. Okay. Now, what are we looking for? We're looking for the mass. Okay, so how do we find the mass? Well, remember, density is equal to mass over volume. Mass was equal to density times the volume. Okay, so our density was 2.47 grams over cubic centimeters, and I need to multiply it times my volume, which is 11.5 milliliters. Now, don't forget, that's also the same as 11.5 cubic centimeters. Now, why do I want to use that? Well, just like math, where numbers on top will cancel out with numbers on the bottom of a denominator, units also do the exact same thing. Okay, so what's the only unit I have left over when I do that? Grams. That's what I'm trying to get to, grams. That's my mass. So 2.47 times 11.5 will give you 28 point, let's call it 41 grams. Okay. Our next problem. Why will a 10-gram ball of clay sink if you put it in a tray of water, but if you flatten out into the shape of a boat, all of a sudden that clay will now float? And remember, density of water is 1.0 grams per ml. Okay. Well, if the ball is sinking, what does that mean? Well, it must mean that the density of the clay has to be greater than the density of the water. Okay. But If all of a sudden the clay decides it's going to float, that means the density of the clay must be less than the density of the water. Now, density of water is always going to be 1.00 grams per ml. It's not going to change. So what must be happening is we're changing the density of the clay. Okay. So what and how are we changing the density of this clay? Well, remember, density is mass over volume. Okay. The mass, we're not going to change. The mass is always going to be 10.00 grams for our clay. So by flattening out and changing the shape of it, the thing that we must be changing is the volume. Okay. So what's going to happen to the volume? Well, in order to make the density go up, the volume would have to go down. But we want the density to decrease. That means we must be making the volume increase. So what are we doing? By making it into the shape of a boat, we are increasing the volume of the clay. Okay, now, how big does the boat have to be? Well, this density has to be less than 1.00 grams per ml if it's going to float. Density has to be greater. So that means this volume here, the volume has to be greater than 10 milliliters. Then the clay will float. If you compact it and it's not big enough, the clay still won't float. Okay, next, metric conversions, our next topic. What's good about using the metric system? Well, everything when we go from one set of units to another set of units based on powers of 10. So all you're doing is when you're changing from one set of grouping to another set of grouping, just moving the decimals. So remember this. Kids have dropped over dead converting metrics. Okay. That is also a useful mnemonic device for remembering what the grouping prefixes are. Kilo, hecta, the over, or basically the 0, is just going to be your base unit, no power. Deci, centi, and milli. Okay. As you work your way to the right, these are getting to be smaller units. As you work your way to the left, these are getting to be bigger units. Just remember that. Okay. So, how big is milli? This is 1/1000th of a unit, or in other words, let's do it this way, 0.001 of a unit. This is 0.01 units. This is 0.1 units. This is basically just ones. Okay. These are tens of the units, these are 100 units, and these are 1,000 of the same units. Okay. So if I have 2.5 hgs, okay, hectograms, how many grams is that supposed to be? Okay. Now, one more thing to remember. I have two capital D's, or two D's. I have one D for deca, one D for deci. Okay. Now, the abbreviation for deca is not DE or DK, it's actually DA. Okay, so if you say DAG, that means decagrams. Or if you say DAL, that means decaliters, etc. Okay. Now, 2.45 hectograms, how many grams is that? Well, we got a real simple way of doing things when we do metric conversions. Whoops. Let's get rid of everything on this slide. Well, just remember and write out the letters. Kids have dropped over dead converting metrics. This is a real simple way to do things like this. Okay. Now, go back to your original number, cross off the last letter. Okay. What you have left over, that is where you're going to start in this series of letters right here. So we are starting at the H. Okay. Cross off the last one that you have here, and notice in this case there's nothing in front. So I got nothing left over. So this is where I need to end up at. Where is this on the scale? Well, that's basically the O. Okay. So I need to get from H to the O. How do I do that? I need to go to the right. How many spaces? 1, 2. So what do? We move the decimal place. We do the exact same thing to the decimal place that we did with our letters to go from H to O, basically. So I move 1, 2 to the right. Decimal place ends up after the 5, so it's 245 grams. Okay, try another one. 8.3 millimeters is equal to how many? And again, here's the DA. It doesn't have to be a capital D, just so long as you see DA, that means we're talking about deca, the capital D here. So 8.3 millimeters, how many decameters is that? Well, we do the same thing. Okay. Kids have dropped over dead converting metrics, KHDODCN, write those letters out, okay. Cross off the last letters. So I am starting at this thing on the left side, which means I'm starting at the M. Okay. And I'm going to the capital D for deca. Now, how do I get from here to here? I move to the left. 1, 2, 3, 4 spaces. So what do? Do the same thing with the decimal point. Okay. Now, I move 1, I run out of numbers. What do? Well, simply put in zeros. 2, 3, 4. Okay. I move 4 spaces from 1, 2, 3, 4. I do the same thing with my decimal, 1, 2, 3, 4. If you move to the left or the right, you run numbers, just simply put in zeros. So this means it's 0.00083 decameters. Okay. Now, a couple other prefixes that you may end up seeing. Mega means you have 1,000,000 things. If you have a megagram, that means you have 1,000,000 grams. Giga is 10 to the 9th, 1 billion. Tera is 10 to the 12th, 1 trillion. Okay. We can have also more units going to the right here. Okay. This is micro. And this is a Greek symbol called mu. Okay. It's basically 1 times 10 to the negative 6th, 1 millionth. Nano is 1 times 10 to the 9th, or 1 billionth. And pico is 1 trillionth, 1 times 10 to the negative 12th. Okay. In other words, you'd need 1 trillion of these things to basically end up with just one of these things here, whatever we're talking about. Okay. Now, what if we want to convert from mega to pico? Well, those don't show up on the scale. Well, all we do is simply put in blank spots, because mega is not right next to kilo. This is 10 to the 3rd. Mega is 10 to the 6th, so you need to go 1, 2, 3 more spaces over. This is 10 to the 9th, so you need 3 more spaces. And you do the exact same thing with the micro, the nano, and the pico. Leave spaces and move over to the right. So here's your review question. What temperature is 20 degrees Celsius going to be in Fahrenheit? Do your calculation, remember which letter you have, and record it.